As an example, I'll do number 6 here. A group of college students eager to get to Florida on a spring break drove the 750-mile trip with only minimal stops. They computed their average speed for the trip to be 55 miles per hour. How many hours did the trip take? So the distance was 750 miles, the average speed was 55 miles per hour, and an equation that relates everything that I have or I'm interested in is this equation. The average speed is equal to the distance over the time. Now, these are not SI units, and that's okay. I can plug in non-SI values. I can plug in miles and miles per hour, but then I just need to be aware that the answers I'm going to get out are not going to be in SI. So just be extra careful to keep track of them. So I want to solve it for t. So right now t is in the denominator. So I'm going to multiply both sides by t. So that way it's at least in the numerator. These will cancel. But now I have a t times the average speed is equal to d. But I would like to get to t all by itself. So now what I'm going to do is divide both sides by the average speed. So then these cancel out. So then what's left over, what I haven't canceled out yet, is time is equal to distance divided by the average speed. Right there. So then I plug in my values. 750 miles divided by 55 miles per hour. Be careful, you've got a fraction in the denominator. So when I do the math on my calculator, I get 13.636, and then I have a miles, which carries through. And then I divide it by a fraction, so I'm going to flip it and multiply. So this is the fraction that was flipped and multiplied. And then it's easier to see that the miles will just cancel out, and I'm left with hours. And the problem asked me how many hours was their car trip. So I just need to round this for sig figs then. Oops, this was 55.0. So they gave us the speed to 3 sig figs. And they gave us 750 miles. And traditionally, we should just call that 2 sig figs, because that 0 looks like it might be a placeholder. If they wanted that 0 to look important and significant to measure, they could have put a decimal behind there, but they didn't. So I'm going to go with 2 sig figs. And so I've rounded my answer to only 2 sig figs. You know, keep the first 2, and then this 3 would round up because that was a 6. It was greater than 5. I'll do number 10. A race car traveling northward on a straight, level track at a constant speed travels 0.750 kilometers in 20 seconds. And both of those look to be 3 sig figs. The return trip over the same track is made in 25 seconds. Also 3 sig figs. Part A. What is the average velocity of the car in meters per second for the first leg of the run, or the first segment? I drew a little sketch where this is my initial position, that's my final position. The displacement is a straight line arrow from initial to final. The distance and the time were given. So to find the average velocity, I'll use this equation, where the average velocity is equal to the displacement divided by the time. And for the displacement, I'm going to plug in the 0.750 kilometers northwards, because the average velocity is supposed to have a direction. I'm like, if you wanted to, you could say that that was the positive direction, the positive y direction. Then you could have just said plus 0.750 kilometers, or you can just say the north, and then we're just going to carry the north through like an extra unit. So I did the division, and I got 0.0375. Keep the kilometers per second, I rewrote them here, and keep the direction. But they asked for this in meters per second in SI units, so we have to convert the kilometers to meters. So I'm going to multiply by conversion factor. So I have kilometers here in the numerator, the top of the fraction. So I want to make sure it ends up in the denominator here. And then I want to convert it to meters, so I need a kilometer to a meter. And then 1 kilometer, which is a longer distance, is equal to 1,000 of the smaller meters. So then kilometers will cancel out. And then we basically multiply this number by 1,000 and carry through our units. 37.5 meters per second north. And I gave that a direction, so that way it's officially a velocity. All right, for part B, what is the average velocity for the total trip? So now what I'm imagining is that I start at the initial position, like I had before, and I would go all the way north, and then I would have to come all the way back south again to get back to my initial position. So my initial position and my final position are the same location. So if I try to draw an arrow from the initial to final position, that arrow doesn't have any length, it's just 0. So the displacement is 0. All right, and then we plug in the information into our equation. The average velocity is equal to the displacement, which was 0 meters. I suppose you could give a direction, but it wouldn't really make sense. Divided by the total time taken. I decided to write out 0 to 3 sig figs, but if you hadn't, I wouldn't really think that was a big deal at all. If you wanted to put a direction on there, I guess you could say no direction or any direction. Again, a direction on 0 doesn't really make sense. Exercise 18. A spaceship hovering over the surface of Mars drops an object from a height of 30 meters. How much longer does it take to reach the surface than if dropped from the same height on Earth? Neglect air resistance in both cases, so that basically means free fall. And then Earth's acceleration will be 9.80 meters per second squared. And the acceleration due to gravity on Mars is 33% of that on Earth. So the distance it fell was 30 meters. The acceleration of Earth is the free fall acceleration, and the acceleration on Mars, due to gravity, is 33%, so 0.33 times what it is on Earth. So I'm going to start off with this equation. The distance it travels is 1/2 times the acceleration times t squared. And that means that it was supposed to have started from rest, which in this case it did, and have a constant acceleration, which in this case it does. So to try to get t all by itself, so I can plug numbers, multiply both sides by 2. Then the 1/2 will cancel out with a 2. And divide both sides by a. So now I've got 2d over a is equal to t squared. And to get t all by itself without the square, we have to take the square root of both sides. So take the square root of the left whole side and take the square root of the right whole side. So then what I end up with is just t, because the square root undoes the square, is equal to the square root of 2d over a. So I'm going to find the time it takes for just the object to fall on Earth. So I'm going to plug in the values for Earth, 2d over the acceleration of Earth. When I do the multiplication and division, I get 6.1224. And the units, the meters carries through. Here I had divided by a fraction, so I'm going to flip it and multiply it. So here's the meters per second squared flipped and multiplied. Then the meters would cancel out. So then if I do the square root of the value, I get 2.47. And square root of seconds squared, I just get seconds. I'm not going to round this yet and call it my final answer. Let's keep going and get to the end first. Do the same thing for Mars, but in this case, we have to change the acceleration value. So that's why that 0.33 is down there. And following that through again, we get 4.307 seconds. But the question was, how much longer did it take on Mars? So let's find out how much longer by doing the time on Mars minus the time it took on Earth. And we get 1.837 seconds. If I go back to the problem, the 30 meters really should just be called 1 sig fig. And so that seems like the limiting precision. So it seems like our answer should only be 1 sig fig. I'm going to keep this digit, but because the next one is greater than a 5, this one rounds up, so I'm just going to say 2 seconds. Exercise 19. For exercise 20, a race car goes around a circular, level or flat track with a diameter of 1.00 kilometers at a constant speed of 90 kilometers per hour. What is the car's centripetal acceleration in meters per second squared? Right. So we have the diameter is 1.00 kilometers, but usually we're going to want to deal with radius. So right now, before I make a mistake with that, I'm going to just quick switch it to radius. And the radius is half of that. And the diameter was 1,000 meters, because it was 1 kilometer. So then the radius is half that, 500 meters. The average speed was 90 kilometers per hour. I'm going to go ahead and just switch this into SI units before I do any other math with it. So I just start out with what I have. And then I'm going to multiply by a conversion factor to change kilometers to meters. 1 kilometer is equal to 1,000 meters. I have kilometers in the numerator and the denominator then, and they cancel out. And then a second conversion factor to change hours into seconds. Hours was in the bottom here, so I want this fraction to have hours in the top. And in 1 hour, there are 3,600 seconds. Hours will cancel out. Type this into a math, right? 90 times 1,000 divided by 3,600 turned out to be 25 meters per second. Turned out to be 25. And I said 25.0 just to kind of keep the 3 sig figs going, so I don't forget about that. And the only units that stuck around were meters per second. Right. So then we were in the case of circular motion at constant speed. So we can say the acceleration is just v squared over r. So we plug in our v, our average speed, 25 meters per second, divided by 5, right? All of that squared, divided by 500 meters. Right. So in circular motion, we can just say the acceleration is equal to v squared over r. The average speed was 25, right? The speed was 25.0 meters per second, all of that squared, divided by the radius of 500 meters. The 25 squared became 625, but the units are also squared, so we end up with meters squared per second squared. Do this division, we end up with 1.25. And for the units, we ended up with a meter squared per second squared. So that's here, meter squared per second squared. But then we also had to divide by meter, so it ended up there. So then one of the meters in the numerator will cancel out with that one, meters per second squared. But if they ask what the acceleration is, that's a vector, we should give it a direction. So let's do this. The centripetal acceleration is 1.25 meters per second squared, and that's 3 sig figs, like the problem was 3 sig figs. And it is pointing to the center of the path, or center of the circle.